Tutorial 6, Part 3, Other Factors Related to Material Failures. Fracture energy and ductile to brittle transition. Fracture energy is the energy required in impact testing to break a small sample, and therefore definitely we can use impact testing to determine the impact energy of a sample. And actually, such energy is comparable with the fracture toughness for different materials, which have a similar trend to the fracture toughness for different materials. Fracture toughness is already introduced in Tutorial 4, and also I have already mentioned it again in the previous part. For a large value of fracture energy, it will have a larger fracture toughness value for a single material. And the reverse is also true. Ductile to brittle transition is a phenomenon for some of the materials. Typically, low strength BCC steel, the body center cubic steels. For higher temperature, those materials will become more ductile, and therefore they will have a more impact energy. And in lower temperature, they will become more brittle, and therefore the impact energy will become less. As you can see from this picture here, A and B, A represent the impact energy trend of a certain material with respect to temperature, and B represent the shear fracture trend with respect to temperature. The impact energy, as I've already mentioned, in higher temperature, here, for example, in 100 degrees Celsius, you can see that the impact energy is approximately 100. And for lower temperature, let's say 0 degrees Celsius, the fracture energy is more than 10. And for B is the shear fracture percentage. For higher shear fracture percentage, you can consider it as it has a higher percentage of ductile fracture. And for a lower percentage, definitely it has a lower percentage of ductile fracture or a higher percentage of brittle fracture. As you can see that there is a similar trend or comparable trend of these two. Basically, for some of the materials there, they will experience a ductile to brittle transition with respect to temperature. When the temperature is high, they will become more ductile, and their fracture energy will be larger, and their failure mode become ductile fracture. And the reverse is also generally true. Fatigue and cyclic loading. Fatigue is a form of failures that occurs in structure subject to a dynamic and fluctuating stresses. And based on this definition, a cyclic loading will cause fatigue for the loading materials. What is a cyclic loading? You can see from the graph here. You can see that it is a sinusoidal wave. It's one kind of cyclic loading. The sign of that loading is constantly reversed in a periodically way. The stress value is first positive and then negative, and then positive and then negative. It is just like when you try to bend a small piece of metal strip forward and backward, and basically the applied stress is fluctuating, and therefore the applied strain or the strain of the material is also fluctuating, and therefore this is what I call cyclic loading. And as you experience that, when you bend a metal strip forward and backward, it will eventually break in a very quick manner. And that is basically what fatigue means. We can use SN curve to decide the maximum allowable stress amplitudes allowed in cyclic loadings. The loading amplitudes is basically defined as the maximum applied stress minus the minimum applied stress over 2. And we can use two ways. The first way is the expected working cycles is given. We need to decide the maximum stress amplitude, or the stress amplitude is given and the maximum allowable working cycles is our point of interest. And here is an example of such SN curve. On the x-axis here, it is the cycles to failure and in log scale, and the y-axis here is the stress amplitude. It is very straightforward, and actually we can have some designs to prevent failures. The first thing is geometric design. As we have already introduced the stress concentration factor at that positions around some geometric features. For example, at sharp corners, there is likely to have a stress concentration, which the applied stress will be amplified. So, in the design of some objects containing some stress concentrations, such as sharp corners and other geometric features, we should try to eliminating or minimizing those stress concentrators. For example, using fillets at those sharp corners. The second method is surface treatment. As the crack formation at surface is likely to happen in the usage of those designed products or objects. As we have already introduced, those small cracks which are not visible to naked eyes will still affect the maximum stress we can apply in that particular object by the definition of the fracture toughness. And therefore, if we try to prevent those formation of the cracks using surface hardening, we can improve or we can prevent the failure of that particular object. Surface hardening, we can use coating using carbon and nitrogen atom. Another method is introduce a compressive stress at the surface. For example, using shot peening and laser shot peening, which can partially remove the external tensile stress applied because compressive stresses is already induced at the surface. When the applied load is external tensile stress, it can partially neglect the external tensile stress. Creep. Creep basically means that for a material, even if you apply a constant stress, over time, over a prolonged period of time. The strength of that material is not constant with regard to time. That means, for example, if you try to pull a bar and hold this force for a prolonged period of time, even, let's say, the force or the stress applied is well below the limit, which is the yield stress for that material, the length of that material could still increase over the time. And this will happen at an indefinite temperature, usually at temperature higher than 0.4, the melting point of that particular material. And actually, the larger the grain size within the material, the better a material's resistant to creep. For example, for those aircraft turbines, their working condition is usually at a higher temperature, at a very high temperature, due to the air resistance, the friction, and those fuels, and the prevention of creep is a serious issue for those design of the aircraft turbine. And actually, in modern design of those turbines, we use single crystal turbine. And actually, that's basically why, or basically an application of this principle. Larger grain size, the better materials resistant to creep.